Up until now we've been noodling or velluming around mainly in SOPs, with a few additions where we dove into the Vellum SOP solver. However, Vellum gets really powerful when you use it within DOPNets. And yes, I have a weird relation with DOPs and DOPNets. You can watch some nerd rounds we did on them. You can watch Manuel's intro into how DOPs works. But what I'll do here is just give you a quick intro of how to use Vellum within a DOPNet. So let's drop down a GeoNode, dive in. And what I want to do is shoot those soft body spheres together. So let's drop down a sphere, scale that down to 0.1, set its primitive type to polygon, increase its frequency to 3, move it to the side a bit. So let's say to -1, or even a bit further, to -3, like this. And now what I want to do is write some velocity vectors on those individual points here, and they should all point in the same direction. That's the direction that we're going to shoot this sphere. So let's drop down a point wrangle. You can do this with a point box as well. And what I want to do here is I want to specify a general direction in which this thing should move. So vector dir for direction equals 2, and let's just set it to 1 along the x-axis, 1 along the y-axis, and 0 along z. So it's pointing diagonally in this direction here. Let's just write that to a vector called v, and highlight our point wrangle, click on the info symbol, and then click on the V to visualize our vectors here. Okay, now what I want to do is, over time, I want to wiggle them around within a given cone around this direction. So it basically shoots in the same direction, but with a bit of variation over time. And for that, I'm going to create another vector, call it vel for velocity, and I'm going to use the sample direction cone function. Let's just open its help page, and this thing takes 3 arguments: the center, so that's the center of the direction that we specified up here, the maximum angle in radians, which it can deviate from this center here, and then a random vector of 2 called u, which works like a seed. Our center is our direction vector, then our max angle, let's call this max a, and then our seed u. So we need to create the max angle and the u, so let's create a float called max a for max angle, and this is in radians, so we want the radians of, say, 5 degrees. So it'll vary around 5 degrees around this center vector here, and then let's create a vector 2, call it u, and this one should be random, and we'll use our frame count plus some seed to generate a random number, a random vector. And now we can set our v to vel, which we sampled here, close this one and hit play before just toggle the real time here. And we can see this wiggles around a bit. Exactly what we want. Let's duplicate those 2 nodes, move this sphere over to 3, and then let's just invert our x direction here so it points in the opposite direction, and let's just change our seed here a bit and merge those 2 spheres with their velocity vectors. Like this, and you can see both wiggle around. Let's set up a soft body, a Vellum soft body, and within our Vellum struts here, I'd like to set the stiffness to 10,000 instead of 10, so it is not that squishy. Okay, let's get started using the DOPNet. Let's just first disable the visualization here, and then drop down a DOPNet. And the first thing we could do, or we could feel tempted to do, and let's just do that, is wire in our Vellum into the 3 first slots and then dive into the DOPNet. As Manuel mentioned in his intro to DOPs, and as we discussed in our nerd round, DOPs works a bit differently than SOPs. So what we're doing here is, on the one hand, setting up an object which contains the simulated object, the simulated geometry, and on the other hand, a description of what should be done with this object and with the elements contained within that object. And I'd like to start from the bottom up. So what we'll have is a general gravity pulling stuff down. Then we'll have a collider, a ground plane, so we're going to merge those in. Merging just combines different solvers, different geometries here. So we're going to use a static solver here, which will wire into the merge, and then a ground plane, which will wire into the static solver. Let's move that down to, say, -1, and then drop down our Vellum solver. Wire this into the merge too, and this one needs a Vellum object. So this is the object which stores the simulation geometry. And that is all we need for a very basic Vellum setup. So let's just hit play. We can see, yes, on the one hand they fall down, on the other hand our velocity is a bit too low, so let's go up one level, and within the point triangle here, multiply our velocity vector with, I don't know, maybe 8. Like this, copy this, and over here, paste this too, highlight our .NET, and hit play one more time. Yeah, that is better. Let's just save this and dive back into our .NET here. Although this works, and it works okay, what we want is we want to continuously or intermittently shoot out those spheres into our scene. And for that, we need a vellum source, which we're going to wire into the last slot of our vellum solver like this. And now let's have a closer look at what all those nodes do in here. So again, the output just collects the results of the simulation. The gravity pulls down everything. The merge is telling Houdini to execute first this branch here and then this branch here. So first, the static solver and the ground plane get executed, which will just take care of having something to collide with, and then the vellum solver is executed. In our previous setup, the only thing that was hooked up to this vellum solver was the vellum object, and in here we have an initial data tab. And by default, the initial geometry and the initial constraint data is already linked up to be the first 2 input slots of our .NET. And what I'll do here is just steal those by cutting them, and then heading over to our vellum source, and within the source tab, let's paste this as our subpath, and let's steal the initial constraints too, cut that, and copy it into our constraint subpath here. So we are linking to the first 2 input slots of our .NET here. And the vellum source by default is set up to be active and emit only once. So if we hit play, we don't see any difference compared to our previous setup. So let's reset this, and instead let's switch this to continuous and hit play again. So what we see now is every frame a sphere is emitted. And while this is arguably in the direction of what we want to achieve, we don't want to emit a sphere each frame. So let's instead write an HScript expression within the activation tab here. So we want to check if our frame number modulo 5 equals to 0. And I explained the modulo function in our displacement tutorial that we recently released on our free stream. What we are doing here is dividing our current frame number by 5 and returning the rest of an integer division. So every 5th frame, this will equal to 0, and that's what we're checking. So we should emit a sphere every 5th frame. Let's hit play. And that's exactly what we wanted. Maybe let's emit a sphere every 4th frame, like this. Play again. That's still working. And now let's set up some constraints in here, because I thought it'd be funny to have some glue constraints so those spheres start sticking together. And let's drop down a vellum constraint sub here. And there are several ways how you could wire this in. The most basic, most blatantly obvious way would be to just wire this in here. What we could also do is drop down a merge, wire this in between, and then wire it up like this. So those would yield the same result. For now, let's just stick it in here and set this up to be a glue constraint. Let's set the maximum search distance to 0.05 and have 2 constraints per point, and maybe for good measure enable the braking and set it to 0.001. Let's check if that works. Also, up here, we want to create those constraints not only on the first frame, on the creation frame, but each frame. And you might even consider for later, if you're getting weird artifacts or weird behavior in the simulation, to set this to each substep, if you should dial up the substeps on the vellum solver. So let's set them for each frame for now, and hit play. So you can see we're getting this clumpy behavior where some of those stick together. And for now, this is pretty much behaving as I'd expected. As mentioned, it could happen that within the vellum solver you need to dial up the substeps and maybe decrease the constraint iterations, and then it could make sense that within the vellum constraints you'd select create constraints on each substep, not on each frame. However, for now this is working, so that is my basic setup for vellum in DOPS. Let's add a few bits to it, reset this to frame 0, go up 1 level, and I want to copy all those here. So that's where I set up my 2 emitters. Instead of having those on the x-axis, I want to have them perpendicular, so on the z-axis. So let's move our sphere to -3 on the z-axis, and within the point triangle, let's set our x component to 0 and our z component to 1. Also, let's change the seed for our random generator and do the same thing with the other sphere here. So center 0, 0, 3, and then let's set our direction to 0, 1, -1 and change the seed here. Let's highlight our velocity. That is working. And what I want to do now is, while I emit those spheres here every 4th frame, let's say I want to emit those spheres here in between. So what I'll do is copy those 2 vellum constraints here to configure those spheres identically as our main spheres, and then drop down 2 nulls here. Call one out_geo and the other one out_constru for constraints. Wire these like this, and then dive into our .NET. And now what I want to do is create a second vellum source for those additional 2 spheres that I created. So copy this over here, and let's check if the modulo of our frames is not 0 but 2. So this will offset the emission on this vellum source by 2 frames here. And then we want to feed it into the same solver here, into the same network here. And that's finally done with the merge, which I'll wire in between here and then wire this up. The final thing I need to do in our vellum source is not point our SOP and constraint SOP to our first and second slot of our .NET, but let's just select our out_geo and our out_constraint respectively here. Save this and hit play. So that is still behaving as I'd expected. Still a nice bit of clumping here due to the glue constraints. And let's talk this .NET over one more time. So what we're doing here is we're building kind of a scene description tree. And this tree is executed top to bottom, left to right. So the first thing that's been executed is this ground plane and this static solver. Then we'll create a vellum object, and then this solver here gets evaluated. So we are going up this branch here, here, and here, and the first thing it evaluates is this vellum source. So we are creating geometry and constraints. Second thing it evaluates is this second source here. So if this condition here is met, we're also creating geometry and constraints. Then we will dynamically at each frame look if there is geometry nearby, which we should stick to and create glue constraints, and feed that into a vellum solver, which then solves the physics of it. The whole simulation is subjected to gravity due to the gravity node here, and then is output to Houdini. And this is the only weird thing that I had to learn, or maybe the major weird thing about DOPS that I had to learn when I began using it. It's that you are not building one single geometry stream, but more like a tree-like description of your simulation. One thing to mention here is that those gray slots here are objects, and objects contain data, simulation data, while the pink slots here are particles. So those pink slots are used to set up particle data within our vellum object. And that is due to the fact that vellum in its heart is XPVD, so position-based dynamics. It's just particles connected with some constraint geometry, which at the core of it is what makes vellum so fast compared to other solvers. So that was a first glimpse into using vellums in DOPS, and we are going to have a look at a very practical use case for this in our next video tutorial. See you then.